Today's lesson deals with acids and bases. You're already familiar with a lot of things about these. So, what are some basic properties of acids? They give many foods a sour or tart taste. When in solution, they conduct electricity because there are ions present. We can call those weak or strong depending on how much they ionize. They're able to dissolve many metals. We all know lots of great examples from movies where we see this. And they change the colors of indicators. In particular, acids turn litmus paper red. So if it's red litmus paper, it stays red. If it was blue, it will turn it red. Okay, some examples of acids. Many of our foods contain acid. So vinegar, that would be acetic, also known as ethanoic acid. All our citrus fruits have citric acid in them. Apples and grapes, malic acid. And interesting to know that it is when the hydrogen ions from the acid in the food react with the protein molecules in your taste cells. These cause the protein molecule to change shape, and that's what triggers an impulse to your nerve endings and to the brain, and you're like, oh, I ate something sour. Okay, some other examples. Your component of stomach acid is essentially hydrochloric acid. We should mention the most widely produced chemical, not just acid, chemical in the U.S. is sulfuric acid. It's important in many manufacturing processes. And nitric acid is one that we very commonly find used in chemical laboratories. What can we say about bases? Bases have a bitter taste. They feel slippery. They change the color of indicators. If we're talking about litmus paper, it turns paper blue, so blue paper stays blue. If it was red, it will turn it blue. They too can produce ions, and so are electrolytes, and we too can classify them as strong or weak. Examples of bases are certainly less common in food, and that's probably due to natural selection as we adapted to protect ourselves from what are known as alkaloids. These are organic bases that happen to be found in many poisonous plants. A very common one would be hemlock. One of the few foods that does indeed contain a base is coffee. And that is why sometimes you get to the end of the grinds and that it's a very bitter taste. Soaps contain bases, as do many household cleaners, in particular ammonia. You can see that many of the bases are indeed dangerous. Drano would be a base. However, we also have baking soda, which is a base. And this we find in many different baking goods. In a first-year chem class, we are going to use what is known as the Arrhenius definition for an acid and a base. It's a rather simple definition. We're saying that acids are compounds that produce hydrogen ions when in solution, while bases are compounds that produce hydroxide ions in aqueous solution. Important to note that just because I see a hydrogen in a formula, that is not what makes it an acid, because many hydrogens in a formula, for example, methane, CH4, those hydrogens are not ionizable, and so methane is not defined as an acid. Now, this is the definition we're going to use in this class, but very important to point out that there are some basic problems with this definition. The biggest one being in regard to bases. There are several bases that if I follow this definition, it does not meet the ionizable hydroxide. For example, I look at sodium carbonate, which is indeed basic, as well as ammonia, NH3. I do not even see a hydroxide in the formula. It was the Danish chemist Bronsted and an English chemist Lowry who independently proposed a new definition known as the Bronsted-Lowry definition. However, that is not one that we are going to use here in a first-year chem class. Those of you taking Chem 2 next year or Biochem will come across the Bronsted-Lowry definition. It's a little broader and so includes things such as sodium and carbonate and ammonia in their definition. So we said that we can have strong acids and strong bases. How do we decide? Let's look at the acids first. So strong acids are acids that ionize 100%. That means they completely break into their components. Easy, there are only 6. Hydrochloric acid, hydrobromic acid, hydroiodic, nitric, perchloric, and sulfuric acids. So if you're not one of those big 6, you are automatically just classified as a weak acid. It's that simple in defining them. So the hydrogen ion concentration for a strong acid is going to be whatever the molarity on that label reads, because it completely breaks into a hydrogen and a chloride, a hydrogen and a bromide, a hydrogen and an iodide, a hydrogen and a nitrate, etc. The hydrogen ion for a weak acid is just going to be something less than the molarity of the label. Let's look at some examples where we would determine the hydrogen ion concentration in an acid solution. First of all, let's take note of the H3O plus bracket here in the header. This is properly called the hydronium ion. It is the same as what we commonly call the hydrogen ion. What it is a water molecule to which the hydrogen ion has become attached as it is ionized in the water. So we would have the H, 3 H's, and O, and it would now be positively charged. So very correctly, you're going to see the hydronium ion as a substitute for writing H+. However, we very commonly just write H+ concentration because it is simpler. The square brackets around simply mean concentration in terms of molarity. So let's find the hydrogen ion concentration for 1.5 molar HCl. So first of all, we have to look at this and recognize that this is a strong acid. I know it's a strong acid because it is in my group of the big 6. That means it's going to ionize 100%. It will break into a hydrogen ion and a chloride ion. So whatever is on the label is indeed the concentration of the hydrogen ion. So I would simply write that as either H3O plus, or you can be lazy and write H plus, and it would equal 1.5 molar for this example. Another example, 3.0 molar acetic acid, HC2H3O2. Notice this is not one of the big 6. It is a weak acid. So it is not going to ionize 100%, and we're simply going to say the concentration is less than what is on the label, the 3.0 molar. Being able to actually calculate that is way beyond the scope of a first-year chem class. That's something that will be addressed in an advanced chem class. 2.5 molar HNO3. Hopefully you recognize this as one of the big 6. It's a strong acid, meaning it ionizes 100%, and so the hydrogen ion concentration is exactly what is written on the label. That is 2.5 molar. It's that simple. We can say the very same thing about strong bases. Strong bases ionize 100%. So what is a strong base? Not quite as simple as the big 6 for acids, but again, it's very limited. Any base that is made from a metal in group 1, so lithium, sodium, potassium, etc. And in group 2, it is only those bases that are made with strontium, calcium, and barium. And if you look at the periodic table, you'll see calcium, strontium, and barium are all together in periods 4 through 6. So helpful in looking at the periodic table to get that visual. If you are not one of those bases, you are considered a weak base because you do not ionize 100%. So again, we're going to see if we want to know the hydroxide ion concentration, it will be exactly what is on the label for the strong bases, but we're going to have to watch out for the subscripts in strontium, calcium, and barium as we make those adjustments. For a weak base, we're simply going to say that it is something less than what is on the label. So let's look at determining the hydroxide ion concentration for 2.25 molar KOH. I recognize, hopefully, that this is a strong base. I see potassium, that is a group 1 metal, which means this will ionize 100%. It will become a K plus and a hydroxide ion, and exactly what I have here will be the concentration of the hydroxide. So our hydroxide ion concentration will be 2.25 molar. Let's look at a second example. 0.35 molar CH3NH2. Now please don't worry that you recognize this as a base. I will be telling you it's a base and simply asking you to find the concentration of the hydroxide. This is an example where the Arrhenius definition falls short. We don't even see the OH. That's why I'll help you out. So this is a weak base because I do not have a group 1 or the 3 group 2 metals with a hydroxide. Simply means it won't ionize 100%. I told you it's a base, so the hydroxide ion concentration is just less than the number posted on the label. One last example. Let's find the hydroxide ion concentration for strontium hydroxide. We need to recognize that this is a strong base because I have strontium here, one of the group 2 metals that we said was a strong base. Pay particular attention to our subscript here. That means when our strontium ionizes, we're going to get a strontium ion and 2 hydroxide ions. So our hydroxide ion concentration, just as we talked about in our last chapter, is going to be twice what is on the label. So the hydroxide ion concentration would be 0.050 molar hydroxide. It would really just be strontium hydroxide, calcium hydroxide, and barium hydroxide where I would have to make that correction for multiplying by 2 with 100% ionization. All right, so that's all we're going to look at in terms of talking about acids and bases and determining whether they're strong acids, strong bases, and measuring their specific ion concentration.